Alright, class, so we are going to pick up where we left off yesterday or on Wednesday, going through some initial pre-questions before we get into some new material. So just to review, what two forces, or when two forces are applied in opposite directions along the long axis of the bone, it is considered what type of load? And I'll give you a second to think about it, and the answer to this is going to be tension. Okay? Forces acting in opposite directions causing tension on the longer side and compression on the smaller side is considered what type of load? So in this case, we have three forces total. Two of them are going in one direction, one is going in the opposite direction, creating compression on one side and tension on the other, and that, of course, is going to be bending. Right, next, adult bone is stronger in blank and weaker in blank. So in general, specifically when we were talking about the bending type of force, adult bone is going to be stronger in compression and weaker in tension. And as we discussed in class, that is going to be just the opposite when it comes to child or potentially even adolescent bone. What is the intensity of a distributed force? So this is otherwise considered how much load a tissue can withstand, or how much numerical force can actually be placed on some type of tissue, and that is going to be the stress. The measure of the degree of deformation of a tissue, or how much change in shape a tissue can actually take, is going to be strain. The area under the curve of the stress strain curve, we talked about it on Wednesday, but it is considered Young's modulus, right? And conceptually, that represents how much potential energy is actually stored in some tissue when it is stretched or when it changes shape, okay? So the more that we change a tissue's shape, the more that we stretch it, the higher that potential energy is going to get, right? If you think about the stress strain curve itself, on our x-axis, we have our strain. And the further and further we go to the right of that graph, right, the further and further we change the shape of a tissue, the more area under the curve we're going to have, right? And that represents a greater potential energy that is stored in that tissue. Now, when we have a stress strain curve, it can represent multiple types of tissues, right? So when we have a tissue that is very stiff, such as bone, versus a tissue that is more pliable and can be stretched and change shape a good bit, like a tendon or a ligament, those curves are going to look different. So with bone, we are going to have a steeper initial slope, a shorter elastic region, and our yield point and our failure point are going to be closer to zero on the strain side. So if we're looking at our graph, right, and we have strain on the x-axis, the yield point and the failure point are going to be closer to zero on that x-axis, all right? Now, with a tendon or a ligament, that initial slope is going to be flatter, right? We can stretch tendons and ligaments a lot, but they really can't withstand a lot of force being applied to them, okay? So with that, we will have a flat initial slope, a larger or wider elastic region, and therefore our yield point, which separates our elastic and plastic regions, as well as the failure point, are going to be further away from zero on that strain or x-axis. So we're going to be further to the right on that stress strain curve. If you have any questions about any of these review points, please email me. I may have access to my phone tomorrow. I'm not really sure, but if I do, I will certainly get back to you as soon as I can. Okay. Now, moving into some new material. First, we're going to talk about some unique mechanics of bone. All right. The first characteristic we're going to discuss is what's called anisotropic, all right? So that means that bone can respond differently depending on the direction of a load, All right, so the type of fracture or break or deformation of any kind that we are going to see in bone is directly coming from how force is actually applied. All right, we know that we are stronger in compression, especially compared to a shear force. All right, so when we have a compressive force along the long axis of a bone, we may see some very minimal deformation there. However, if we have some type of force that is applied in opposite directions across that long axis or 90 degrees to that long axis, we are probably going to see more deformation and a potential fracture from that type of shear force, right? The second characteristic is called viscoelasticity. Now, strictly, this means that a bone is going to respond differently depending on the rate of some type of load application. And what I mean by the rate of load application is simply how long is a certain load or a certain force applied, right? In duration, in seconds, in minutes, in hours, right? How long is a specific load actually applied to a tissue? Now, when we have a slowly applied load, right? So say we have 20 newtons of force that is applied over a long duration of time. It's applied slowly, okay? It's not some sudden, instant movement, right? When we have a slowly applied load, our bone is going to resist strain or resist deformation less than a rapidly applied load, right? So to put it in a different way, if a really high force is applied very suddenly, then we are actually going to be able to withstand that load better than if that same load were applied over a long amount of time, okay? So if we have an increased rate, right, it's applied fast and it's applied hard, our strength is actually going to increase, right? The amount we can handle instantaneously actually goes up, right? Because the stiffness of our bone is actually going to increase. So when we look at the graph, if I can get my pointer here, if we look at the graph here, when we have higher stress, right, so higher on the y-axis and less strain compared to the others, that is going to give us an increased loading rate, all right? And in that way, with bone specifically, our bone can handle increased rate of load way better than it can a slowly applied high force over a long period of time, okay? We can handle those sudden bursts of high forces. We can't handle long-term or longer, I guess, being exposed to larger forces longer, okay? Now, when it comes to bone atrophy, that is strictly the weakening or shrinking of bone, okay? Now, what that looks like is specifically in swimmers or cyclists and astronauts, we are actually going to see, we are actually going to see some type of change in the bone itself, right? Meaning that the density of the bone is going to decrease, all right? I thought I had an image for this, but I guess I don't. Swimmers, cyclists, and astronauts specifically have a diminished density of bone, all right? That bone atrophies, gets weakened, or the density goes down because those particular sports are not weight bearing, all right? If you think about a swimmer or a cyclist training for certain events, they are less often weight bearing compared to a cross country runner or an Olympic weightlifter, right? Or a football player, okay? Astronauts obviously have a little bit different situation they do have an extreme situation in which they are not exposed to gravity. All right, so physically, they are non-weight bearing constantly, right, during those specific environments. So obviously, swimmers and cyclists are not going to have as much atrophy as populations such as astronauts, right, or someone who is exposed to an extreme situation such as that. However, they still do have some type of minimal bone density, or decrease in bone density, I should say, compared to a typical weight-bearing athlete. Now, we can also have bone atrophy due to age. So, as we age, we can, or most likely will be, diagnosed at some point in our life with what's called osteopenia, right? Now, this is simply a reduced bone mineral density for the age range that we are in, all right, based on some type of standardized data, okay? Now, this simply means a reduction. It doesn't mean a drastic reduction. It simply means that you are under the curve for the standard bone mineral density based on your age, okay? Now, on the other hand, a significant loss of bone or a significant atrophy is going to lead to what's called osteoporosis, right? Now, at this point, you can see here on the picture to the right, we have normal bone, osteopenia that you can see a little bit more holes going on, right? It's less dense material, but not extremely drastic. Osteoporosis, though, is a pretty significant reduction, right? We see a lot more darker brown space in that image. And then, of course, severe osteoporosis is going to be very, very minimal bone density. And within osteoporosis, and especially severe osteoporosis, we are going to pretty significantly increase our risk of some type of bone fracture or bone break. Now, bone fractures in general are by and large the most common injury to bone. It is simply a disruption in the structural continuity of bone. So, in some form or fashion, that hard, stiff material is going to be deformed in some way. All right, even a small way is considered a fracture. It does occur at the failure point of the stress-strain curve. Now, the fractures that we are going to talk about today, they're not stress fractures, they are actual bone breaks, right? So, in that sense, each of these types of fractures that we're going to go over does occur at the failure point of that stress-strain curve. Now, remember, the plastic region of that stress-strain curve does represent the region in which you could have some deformation to where that bone is not going to go back to its original shape, right? So in that region, yes, we may have a stress fracture or something very small and minute, all right? But the fractures we're going to talk about do occur at the failure point of that stress-strain curve. Now, there are different types of fractures based on the type of load that bone undergoes. One of the ways that we can look at how a fracture occurs is called the mechanism of injury, right? The MOI. So anytime you see MOI on a slide, that's what it means. And that is strictly how a fracture or an injury occurs on a mechanical level, right? Where are the forces applied and how are they applied to cause a certain injury? Sometimes our mechanism of injury can be very specific. Others, it can be more generalized. It strictly depends on the type of injury, in our case for bone, the type of fracture itself, okay? So, looking at closed or what's called a simple fracture first, this is simply a fracture in which the bone does not penetrate the skin. So it can be transverse, straight across or 90 degrees to that long axis of the bone, or it can be what's called oblique, where it's kind of at an angle going across that long axis. Now in this case, our mechanism of injury for this type of fracture is some type of blunt force, or it's a high amount of force distributed over a long amount of time. We talked about with our viscoelasticity, if a high amount of force is distributed over a long amount of time, we're probably going to see some type of fracture because our bone cannot handle that. Now, with a transverse versus oblique fracture, it strictly depends on how the load is actually applied, right? Is it applied directly 90 degrees to the long axis of the bone, or is it applied somewhat at an angle, right? If it's applied at an angle, obviously we're going to have a more chance of getting an oblique fracture rather than a transverse. If it's directly 90 degrees, we may see some type of transverse. Realistically, we will see more oblique closed fractures than we ever will transverse, right? There's not many situations in which the fracture is perfectly 90 degrees to the long axis of that bone. Next, what's called a comminuted fracture is when we have a break that is fragmented into more than two pieces, right? This is fairly common during increased loading rates, all right? So if we are stronger, all right, when we are exposed to a high force in a sudden amount of time or a small amount of time, right? We are strong in that. However, if it is beyond what our bone can withstand, right? If it's beyond that plastic region at the ultimate failure as far as the force itself, right? The amount of force applied, then we are going to have what's called extreme blunt force trauma, right? And that is going to lead to more than two fragmented pieces. So car accidents and really extreme falls, such as off of some type of high surface like a ladder, if you're working on a roof and you fall and you land and break your leg, you're probably going to have a fracture like this. But again, it's because of strictly the high amount of force that is beyond our ultimate failure point on that stress strain curve. An avulsion fracture. So this is a really interesting type of injury because it's actually more common than you would think. But what happens is instead of a tendon or a ligament undergoing an injury itself, if there is some type of sudden force application, specifically in changing direction, if you have a small or a diminished bone mineral density especially, the tendon or ligament can actually pull a piece of the bone off rather than the tendon or ligament undergoing the injury itself. So again, most of the time it happens with a sudden change of direction. Obviously, it would also have to have a high amount of force. So when we think about a baseball pitcher, right, they're continually changing direction, specifically of their arm, right? This particular injury is, it's not letting me go back. The particular injury on that slide was the medial elbow, right? So the UCL, which is your ulnar collateral ligament, can actually pull a piece of your humerus off under certain circumstances where we have a high amount of force and obviously a large amount of rotation. Okay. All right. I'm sorry about the slideshow here. I don't know why it's not letting me go back. But moving on to green stick fracture. This is what's called an incomplete fracture. So it does not break into pieces per se. Now, this is going to be a one-sided fracture. So the break itself only happens on one side of the bone. It doesn't go all the way through. And the other side remains simply bent. All right? There's not a fracture through to the other side. It is more common in children because they have more collagen and less mineralization within their bone at that point in life. Now, it is common to see this type of fracture with bowing, or a bow-legged individual, right? If you see an infant or a toddler who seemingly has rounded or bowed lower extremities, like whether it's, most of the time it's kind of the shin area, it could potentially lead to some type of green stick fracture if they do not mature in the correct manner, especially physiologically with the mineral and the collagen within the bone. But most common, by and large, with children. Now, the mechanism of injury with a green stick fracture is from falling on an outstretched hand. So, if you ever see the acronym FOOSH, that simply means falling on an outstretched hand. Okay. Now, a spiral fracture is something it's actually really interesting. It comes from extreme force in a torsion manner, so a twisting manner, on a long bone. All right. So the mechanism of injury for this particular fracture is that the segment is twisted with a great amount of force. And what's really interesting with this particular injury is that it's actually, I don't want to say common in sports, but it actually, if you play a sport that has a lot of rotation at really high forces, you could be more susceptible to this type of injury. Now, there is a particular sport that is most commonly associated with spiral fractures, and since we are not in class, obviously we can't have a discussion much about this, but it is actually arm wrestlers, right? If you really want to, you can get on YouTube and look up arm wrestling spiral fracture, and it's very interesting because obviously the humerus is being twisted constantly, right? And these athletes are extremely strong in their upper extremity. So when it happens, it seems very painful. If you look at the image of this X-ray, the fracture is not small, right? There is a very detrimental break that occurs with this type of fracture. All right, next is an impacted fracture, and that's when bone fragments or pieces are actually driven into one another. It can be driven into one another such that they slide past each other, as seen in this this bottom image here. But they can also be driven into each other, meaning a certain bone can be driven into the medullary capsule or space of a joint. So if we, in this particular image, this is our shoulder. All right, the humerus has been driven into the medullary space of that glenohumeral joint, right? So in that way, the fracture itself strictly results from high impact from that extreme compressive force between two pieces of bone or moving into that medullary cavity or joint space. Lastly, we will talk about what's called an open or a compound fracture. This is when we have a fracture that breaks the skin, right? In this manner, we do have an extreme risk of infection, right? Because the bone is exposed, it is torn through soft tissue, and of course has broken the skin. So we have that risk of intruding bacteria or something that could lead to an infection. And because the bone itself is exposed, bone infection is by and large the largest risk here, because if we get an infection in our bone, there is a chance of that you would have to have some type of amputation. Okay. Now, the most common example I like to talk about with this type of fracture was Kevin Ware. He played basketball at Louisville several years ago, and during March Madness one year, he came down. I think he was defending, and he was trying to defend a three-point shot, came down on his leg, and had a complete compound fracture in that tibia. And the tibia itself broke the skin clean. If you guys want to watch it in class on Monday, than we can. But it is a really good example of this type of fracture that seemingly didn't happen from a huge amount of force. But there were some extenuating circumstances with his physiology that potentially led to that injury. So typically, though, with the mechanism of injury here, we have falls, accidents of some kind, like car accident, falling off something, overuse, as well as osteoporosis. So with Kevin Ware specifically, I am not sure exactly what his physiological components, meaning the mineral versus the collagen and the bone mineral density of his skeleton was, but I believe that overuse and some type of physiological component was at play there for a healthy collegiate athlete. So it can happen to anyone, but it's a really extreme type of fracture. So lastly, I want to go over a little bit of your lab for this particular content. It is posted on Canvas, and you can complete it on Word and just upload the document. But first, I'm going to ask you to compare and contrast the expected bone density of a swimming athlete versus an Olympic weightlifter. Explain your reasoning using Wolff's Law and content found using online resources. Also tell me how susceptible to an injury is each of these athletes based on their expected bone density. So I want you to talk to me about Wolff's Law. Tell me how it may or may not apply to a swimming athlete or Olympic weightlifter, right? It is going to apply, but tell me how. And then tell me, based on these differences in bone density between a swimming athlete versus a weightlifter, which of these athletes is more likely to injure themselves or sustain a bone injury specifically based on their projected bone density? Now, I don't want you to give me specific numbers. Just give me a general explanation of increase, decrease, less than, greater than, and it's fine. Number 2, I want you to create a complete stress strain curve comparing skeletal bone, tendons and ligaments, and cartilage. So on this curve, you should have 3 lines, one for each type of tissue. For each line, you need to include the elastic region, the yield point, the plastic region, as well as your failure point. All right. Now, after you do that and you label your graph, you label each of those lines, provide a written explanation of why you drew the graph the way that you did. All right. And I don't want you to just go back to our PowerPoint and say, well, this is how it was in our notes. Yes, that is how it is in our notes. However, be able to explain to me why those lines are different and what it means. Okay? All right, and then lastly, I want you to choose one type of bone fracture discussed from the lecture, provide the mechanism of injury, give me the most common manner in which the injury occurs. So is it by some type of accident? Is it extreme blunt force trauma? Can it happen in sports a lot? And then I want you to tell me the estimated recovery time from the injury. So with question number 3 specifically, I really want you to get on Google, type in whatever fracture you think is the coolest, and try to really research these 3 different components, all right? I don't want you to just take exactly what's on the slide and put it into this lab. That's not the point. I want you to explore it a little bit and really dive deeper into what the mechanism of injury is, the most common manner it happens, and then, of course, the estimated recovery time for the injury. Now, for A and B, you might be thinking, okay, well, what's the difference? Mechanism of injury for our particular lab here. I want you to tell me what type of load is most likely to cause that fracture. Is it torsion? Is it bending? Is it compression? Is it tension? All right. Tell me the type of load and why. All right. Next, When I ask for the most common manner in which it happens, that's when you can talk about accidents or sports or some type of, fall. Okay? So, I hope that this has been clear enough for you guys to understand what you need to do for the lab. If you have a question, please don't hesitate to email me. Like I said, I may have access to my phone. I'm not quite sure yet. So I will email you back as quickly as possible when I receive it. And the lab for this content will be due prior to lab on Monday. So email me if you have any questions. And that is all I have. So I hope you guys have a great weekend, and I'll see you on Monday.